Hello students, today we are here with a new topic, derangements. So all of you may have heard about arrangements but not derangements. So what is derangement? So we are going to learn the definition and then some examples in this topic here. So what is derangement? A derangement is a permutation. We all know that. What is permutation? Permutation is arrangement of objects in a definite order. So arrangement of objects in a definite order is called permutation. So in permutation, ordering is very important. അത് വളരെ ഇമ്പോർട്ടൻ്റ് ആയ ഒരു കാര്യമാണ്. ഒരു derangement എന്ന് പറയുമ്പോൾ it is a permutation. What is permutation? It is arrangement of objects in a definite order. അപ്പോൾ ordering is very important in this case. Here, derangement is a permutation of objects that leaves no objects in its original position. So here derangement, for example, ഒരു example ഒരു 1 2 3 4 5, when you take like this 1 2 3 4 5, so we all know that 1 should be in the first position, 2 should be in the second position. This is the correct order. ഇതാണ് ഇതിൻ്റെ ഓർഡറിങ്. പക്ഷെ derangement എന്ന് പറയുമ്പോൾ ഏത് ഒരു ഒബ്ജക്റ്റ് എടുത്താലും ഏതൊരു നമ്പർ എടുത്താലും ശരി, ഏതൊരു ഒബ്ജക്റ്റ് എടുത്താലും അത് അതിൻ്റെ പൊസിഷനിൽ വരാൻ പാടില്ല. അതല്ലാതെ വേറെ ഏത് പൊസിഷനിൽ വേണമെങ്കിലും വരാം. സോ നോ ഒബ്ജക്ട്സ്, ഒരു ഒബ്ജക്റ്റും അതിൻ്റെ പൊസിഷനിൽ വരാൻ പാടില്ല. അങ്ങനെ ഒരു അറേഞ്ച്മെന്റ് നമുക്ക് കിട്ടുവാണെങ്കിൽ ദാറ്റ് അറേഞ്ച്മെന്റ് ഇസ് നോൺ ആസ് derangement. ഫോർ എക്സാമ്പിൾ, ഇപ്പോൾ 1 2 3 4 5, I'm writing like this 1 3 2 5 4. Is this a derangement? No, this is not a derangement because 1 is in its number in the same position. But when you see 2, 3, 4 and 5, that is not in the correct position. 2 and 3 are exchanged, 5 and 4 are exchanged, but 1 is in the correct position, which means that this is not a derangement. So now here, when you consider 1, 2, 3, 4, 5, here I have taken another example, 2, 1, 4, 5, 2, 1, 4, 5, 3. So which means that is it in the correct position? No. 1 in the place of 1, 2. In the place of 2, it is 1. Here, in the place of 3, it is 4. In the place of 4, it is 5. In the place of 5, it is 3. Which means that no object is in the correct position. Which means that this permutation or this arrangement is a derangement of this numbers 1 2 3 4 5. When you consider this permutation of arrangement or this arrangement is a derangement because no number is left in its original position. Now here also we can write more options. We can write many options, but some of the options only is listed here. For example, 1 2 3 4 5. Let us consider like this 2 1 5 4 3. This is also a derangement. Is it? No, because 4 is in its correct position. No. So therefore 2 1 4 5 2 1 5 4 3 is not a derangement because 4 is fixed. Now 1 2 3 4 5. Let us take like this 5 4 3 2 1. This is a derangement because all the numbers are replaced. So no, any of the number is not in the correct position. So here 5 is in the first position, 4 is in the second position. Sorry, this is not a derangement. So we have to write some another method. So 1 2 3 4 5. Let us write like this 5 4 2 3 1. Now let us check. 5 is in the first position, 4 This is not in the correct order. So therefore this is also a derangement, but this is not a derangement. Like this we can write, because if for simple cases we are able to find out the derangements or number of possible derangements, we can find out. So for if you are able to find out the derangements, so then we can write the values as an answer. These are the derangements as the answer, we can write it. But in some situations it is not possible to predict the derangement itself, because when the number of terms are increased, when the number, if it is a small number of terms or small terms are given for a small number of words or whatever it is given here, if it is very small number, then we can calculate the derangement. But it is a very big numbers, we are not able to find the derangement. Maximum up to 5 we are able to find out the derangement. But if it is 6 or 10 or 11 or 12 numbers arrangements, and if I have to find the derangement, means it is not possible to manually, it is not possible to find out the calculation. So for that, such type of situations, we have to find the number of derangements. So in this case, we have to use the method here. There is a theorem introduced here. That theorem statement is, you have to learn the statement. The number of derangements of a set with n elements is dn is equal to n factorial. So derangements are denoted by the symbol dn. That is equal to n factorial into 1 minus 1 by 1 factorial plus 1 by 2 factorial minus 1 by 3 factorial plus etc. minus 1 raised to n into 1 by n factorial. So therefore, we all know that what is e raised to x formula? E raised to x formula is 1 plus x by 1 factorial plus x square by 2 factorial plus x cube by 3 factorial. Similarly, let us write like this. What is the formula for e raised to minus x? This can be written as 1 minus, because alternately it becomes positive and negative. So we can write this as 1 minus x divided by 1 factorial plus x square divided by 2 factorial minus x cube divided by 3 factorial plus etc. Suppose if I replace in the place of x, if I substitute here as minus 1, in the place of x, let us substitute x equal to 1. So therefore, we get here it is equal to 1 minus 1 by 1 factorial. So 1 minus 1 by 1 factorial plus 1 by 2 factorial minus 1 by 3 factorial plus etc. So e raised to minus 1 equal to, this is the formula. So in this expansion, for this expansion, we can substitute this expansion is equal to e raised to minus 1. So this e raised to minus 1 can be replaced as n factorial divided by e. So it becomes to the denominator. So the number of derangements with a set with n elements, for n elements, dn, derangement is denoted by the symbol dn, or sometimes in some cases they may use small letters dn or capital letter, whatever it is we can use. So dn is equal to n factorial divided by e. By using this notation we can find the calculations. Now suppose if I give n equal to 4, then in the place of this expansion, I can replace d4 is equal to, we know that the formula is dn is equal to n factorial into 1 minus 1 by 1 factorial plus 1 by 2 factorial minus 1 by 3 factorial etc. This is the value. So in this, I am going to write the value up to n equal to 4. So n equal to 4 means the term becomes 4 factorial into 1 minus 1 by 1 factorial plus 1 by 2 factorial minus 1 by 3 factorial plus 1 by 4 factorial. Now we all know that 4 factorial is equal to 4 into 3 into 2 into 1, that is equal to 24. So here 1 minus 1, 1 factorial is 1 plus 1 by 2 factorial is 2 minus 1 by 3 factorial is 6 plus 4 factorial is 24. So here you'll be getting, you can use the calculator to find the values. So you will get an answer to from this 24 into 3 by 8. So this you will get an answer of 9. So if n equal to 4. So in this much calculation we are doing this, but when you use the theorem, by using the theorem, we know that dn is equal to n factorial divided by e. So I can replace n is equal to 4 in this formula. I am going to replace n equal to 4 in this formula. Therefore, when n equal to 4, this formula becomes d4 is equal to 4 factorial divided by e. 4 factorial is equal to 24 divided by 2.178. That is equal to approximately, you will get an answer 8.82, which is equal to approximately, you can write, you will get an approximate answer that is equal to 9 ways. You can use either this calculation or this calculation, but one thing is both I am able to do here because in the number of elements is very small, because n is equal to 4 is very small, so I can do both the calculations. But if n is very large, I am not able to do the first calculation, so we have to try the second calculation, will be the easiest method for doing the problems. Now, for example, suppose if I consider 3 elements, let us consider 3 elements 1, 2 and 3. So let us consider 3 elements 1, 2 and 3. We want to find the derangement. So find the derangements of this number. If n equal to 3, then there are, how will you calculate the values? So how many distinct ways are there? How many arrangements are there? We have to know. So because if n equal to 3, we are able to know that if n is equal to 3 means there will be distinct cases. If n is 3 is distinct. So this is a distinct numbers. So therefore there will be a distinct arrangement, which means that first place can be filled in 3 ways, second place can be filled in 2 ways, and the last place can be filled in 1 ways, which means that there are, which is equal to 3 factorial or equal to 6 ways. So there are how many ways? 6 ways. We have to remember that there are 6 ways of arranging the letters. Now let us write what are the 6 ways. So what are the 6 ways here? 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1. Now, in this, see, listen here, I am writing here. Let me write somewhere. So that will be very easy. So, let us take like this. 1, 2, 3. In this, let us take like this. 1, 3, 2. This is not an arrangement because 1 is in the first place. Now, 2, 1, 3. 2, 1, 3 means, no, 3 is in the last place. Now, 2, 3, 1. So, this is a derangement. Okay. Now, 3, 1, 2. 3 is last, comes the first place, 1 in the second place, 2 in the last place. That means this is also a derangement. Now, 3, 2, 1. Is it a derangement? No, because 2 is in the second place. 2 is fixed. So therefore, now how many arrangements are there? The number of arrangements is equal to, how many number of arrangements? There are 6 arrangements, but out of the 6 arrangements, how many derangements are there? Therefore, there are 2 derangements. Let us take the 2 derangements. These are the 2 derangements. So therefore, the number of derangements is equal to 2. This is the case. In another way, we can say without writing all these expansions, all these derangements or all these calculations, I am going to directly apply this in the formula. In another way, we use dn is equal to n factorial divided by e. So therefore, when n is equal to 3, d3 equal to 3 factorial divided by e, which is 6 divided by 2.718, which is 2.208. Approximately, it is equal to two derangements. So directly I am getting, that means without writing the derangements. What are the derangements? Here there are two derangements. One is 2, 3, 1 and another one is 3, 2, 1. These are the two derangements. So I am going to consider, because I am able to find out, because n value is very small, n equal to 3. So I am able to find out. So without finding the derangement, I can say directly by using the formula, I can say that there are two derangements. Now, suppose n is equal to 4. Now, let us expand this. So, therefore, let us make the expansion to be 1, 2, 3 and 4. So, we are considering 4 positions, 1, 2, 3 and 4. Now, here the total number of possibilities or total number of possible arrangements. So, this cases, are they distinct? Yes. So, they are distinct. That means how many number of possible arrangements or the number of permutation. So what is the number of permutation here? Either the total number of possible permutations or number of permutations for this distinct arrangement, because 1, 2, 3 and 4 means they are distinct. So hence the total number of possible arrangements are, what are the possible arrangements for 4 numbers? How many possible arrangements are there totally? 4 factorial equal to, that means the first place can be filled in 4 ways, second place can be filled in 3 ways, and the next place, third place can be filled in 2 ways, and the last place can be filled in 1 way. So 4 into 3 into 2 into 1, which is equal to 4 factorial. Totally 24 ways are there. So for example, for you I have written here the 24 ways. So what are the 24 ways having here? So what are the arrangements? What are the possible 24 arrangements? First we have to list out that, because I'm writing the calculation, because sometimes you may not able to follow this. So for that I have written here all the 24 arrangements. So listen here, these are all the 24 arrangements, not the derangements, all the possible arrangements. Now I have to find out of this 24, out of this 24 arrangement, I have to find out the derangements. Can you understand this? So here we are going to get the derangement from this. So 4 factorial equal to, I don't know how much derangements will be here. I don't know that, but I am doing is, I am going to cross check all the values. So first one is, all are in the first fixed position. Here this is not an arrangement, because 1, 2 is in their position. Here 1 is in the first position. This is not an derangement. This is also not a derangement. 1, 3, 4, 2. Can you take 1, 3? No, 1 is in the first position. Here 1 is in the first position. Here 2 is in the second position. So this is 2, 1, 4, 3. This is a derangement. 2, 1, 3, 4. This is not a derangement. Now this one, 2, 4, 3, 1. Is this a derangement? Yes. No, this is a not a derangement, because 3 is fixed. 2, 4, 1, 3. This is a derangement. 2, 3, 1, 4. 2, 3, 1, 4. See here, 4 is in the last position. So here 2, 3, 4, 1. This is a derangement. Now 3, 1, 4, 2. In this 3, 1, 4, 2. Which is a derangement. 3, 1, 2, 4. No, 4 is in the last position. Here also 4 is in the last position. 3, 2, 4, 1. So 3, 2, 4, 1. Is it a derangement? 3, no, because 2 is in that position. 3, 4, 1, 2. 3, 4, 1, 2 is a derangement. 3, 4, 2, 1. Is it a derangement? Yes, it is a derangement. 3, 4, 2, 1. Yes. Now 4, 1, 2, 3. 4, 1, 2, 3 is a derangement. 4, 1, 3, 2. 4, 1, 3. This is not a derangement. 4, 3, 2, 1. So this is a derangement here. 4, 3, 1, 2. This is also not is a derangement. 4 2 1 3 4 4. This is not a derangement. This is also not a derangement. So out of this, how much is there? How many number of terms? 1 2 3 4 5 6 7. One more is there left over. 7 here, 8 9. So 8 9 terms. See here, the number of derangements are 9 terms I have written here, but 4 is itself we are little bit struggling because we have to write all the 24 terms. For example, for your clarification I have written here. Now in short, I can use this theorem, that is dn is derangement of n terms is equal to n factorial by e, that is equal to into d4. N is equal to 4 means the value is equal to approximately 9 derangements. So you can find out the value. But if n is equal to 5, when coming on to the next case, from here n equal to 5 means let us consider 5 number of terms, 1 2 3 4 and 5, which means that is it possible to find the number of derangements. Now listen here, if 5 is there, n equal to 5 means the number of permutations. So now what is the number? Because all are distinct. So distinct means the number of permutations is equal to. That means all are distinct. The first place can be filled in 5 ways. That is equal to, how can I write this? The first place can be filled in. So this is equal to 5 into first place can be filled in 5 ways, second place can be filled in 4 ways, third place can be filled in 3 ways, fourth place can be filled in 2 ways, and at last in 1 way. That is equal to 5 factorial, which is equal to 120 ways. Is it possible to write? We have to write all the 120. So therefore, because if in such situations we apply this formula, so dn or d5 is equal to 1 factorial divided by 5 factorial divided by the exponential e raised to 1, that is equal to 44.15, approximately 44 derangements are there. So because number of terms, since we consider the number of terms, we round it to an integer, it is 44 derangements. Now here we shall move on to the next example. How many ways can 11 people enter a room and leave with a different hat? So 11 persons are entering a room and they are having a hat and they have to leave with a different hat. That means they have to replace their hat in the room and they have to take a new one. So 11 members are there. How many ways are there? What are the ways? They didn't ask. How many ways are there? A person with hat enters the room. There is alternately another hat. So he picks up the next one and he moves here. So he is having a hat. So he picks up the next hat and also he is leaving the room. So therefore here n is equal to 11. Therefore it is not an arrangement. It is derangement. So from this we can understand that it is derangement. So number of possible derangements is equal to, apply the formula, that is d11 is equal to 11 factorial by e, that is equal to 11 factorial by 2.718. You can write as it is or you can use the calculator and you can write the answer. So this is the next case. Now we shall move on to the next question. A teacher teaches geometry and biology. A teacher is teaching geometry and biology to a class of 12 advanced students in a classroom that only has 12 desks. So how many ways can she assign the students to the desk so that no student is seated in the same desk for both the classes? So she has to assign and she has to check that no student is seated. No student is seated in the same desk. So therefore, how much can be assigned? The teacher can assign how much students, how many number of ways or number of ways to arrange. What are the number of ways to arrange the students? How many number of ways are there? Totally how many number of ways are there? Out of the arrangements only she has to select the arrangement. So how she can arrange, but how many ways are there? So therefore first step, how will you write that here? So here first we can write like this. She can assign the students in 12 factorial ways. So they are distinct. They are distinct cases. So therefore 12 factorial ways. Now here one more condition is given here. No student is seated in the same desk. That is, which means that it is derangement. It is not arrangement. This is derangement. So therefore, that is equal to D12 equal to 12 factorial by E, which is equal to 12 factorial by 2.718. So therefore, here both ways has to happen simultaneously. Therefore, by using, so you have to write, since both this events has to happen, both the events has to happen simultaneously. Event has to happen simultaneously by the rule of product the total number of ways to arrange the students for both the classes is equal to, both the event has to happen simultaneously, which means that this is equal to 12 factorial into 12 factorial by 2.718. So that is equal to, we can simplify and write the answer. So remember that she has to assign the students in 12 ways. They are distinct, and number of, no, and also one more condition, no student is seated in the same desk. So for both the classes, the student must not be seated in the same position. So both the events has to happen simultaneously by the rule of product. The total number of ways to arrange the students for both the classes is equal to 12 factorial into 12 factorial by E, that is equal. You can use the calculator and you can simplify the answer. Now, there is a second part of this question, B part. She has how many ways can she assign the students to the desk? How many ways can she assign the students to the desk so that exactly 6 students occupy the same desk for both the classes? So, how will you do this? Which means that she can assign the students. Here also the same condition. She can assign the students in 12 factorial distinct ways. So this is the first condition as usual. Both the cases we have to consider. Now exactly one more condition is given here. Exactly 6 students occupy the same desk. Out of 12 for both the classes, remaining. So, exactly 6 students occupy the same desk out of the 12 for both the classes. Out of the 12 for both the classes, remaining 6 is there. So, remaining 6 is, so 6 is an arrangement. So, 6 students occupies the same desk, which means that this is arranging the objects. So arranging here, and also it is not given here. They can, the particular ordering is not mentioned here. For 6 students occupies the same desk, but ordering is not mentioned in this case. So ordering is not important. Also 6 students must occupy the same desk only, it is mentioned, but they has to occupy the same position, it is not mentioned here. The ordering is not important, which means that we consider here combination. Remember that we consider this one as combination. And out of the 12, for both the classes remaining, she has 6 students. So remaining 6 students is considered as derangement. So 6 is considered as arrangement and remaining 6 is considered as the derangement. Therefore, the total number of ways is equal to, the total number of ways is equal to 12 factorial, because all the 3 events. So first one, this has to happen simultaneously. Second one, this has to happen simultaneously. And the third one also must happen simultaneously. So first one answer is 12 factorial into, second one answer is 12C6, because 12 students must occupy the same desk but not the same position, because here ordering is not mentioned, which means that combination. So therefore 12C6 into remaining 6 students are there, that is derangement. So therefore it is D6. So 12 factorial into 12C6 means it can be written as 12 factorial by 12 minus 6 factorial into 12 minus 6 factorial into 6 factorial. So we all know that NCR is equal to n factorial by n minus r factorial into r factorial into D6. That is Dn is equal to n factorial by e. So this can be written as 6 factorial by e 2.718. So that is equal to, you can simplify and write the answer. So this is the problem. So in this problem you are having 2 cases, case A and B. So both the cases are here. It is very easy to simplify. Now one more question is given here. What is that? Peggy has 7 books to review for the CH company. The same case only, but here she hires 7 people to review them. She wants to review per book, so that the first week, she gives each person 1 book to read and then redistributes the book at the start of the second week. In how many ways can she make these 2 distributions so that she gets 2 reviews by different people of each book? So this is the condition. You try this question as a homework, so that I think I can give the answer, as the answer is 7 factorial by e will be the answer. You simplify and find out 7 factorial into 7 factorial by e. Read the sentence and you do the problem, work out this. Okay, thank you students.